Next topic, we look at capacitors. So what are capacitors? Just two metal plates separated by a gap. Okay. And when we connect these plates to a battery, to the opposite terminal of a battery, so one plate becomes negatively charged and the other becomes positively charged. So we end up with two oppositely charged plates, and this is what a capacitor is, a charge capacitor. Okay. Now note that there is no current flowing from one plate to the other. Okay. So there is simply charges building up because they're connected to a negative or positive terminal, but there is no current that flows in between the plates. Okay. So we have two plates that have a potential difference between them because they carry charge and they have they're separated by a distance, and the potential difference of these plates must equal the potential difference of the battery, right? So in other words, the capacitor voltage balances out the battery voltage, so there is no current flowing. Okay, so this is how we charge capacitors, connect them to potential sources. Okay, so let's look at how a capacitor gets charged. So here we have a capacitor on the slide, and let's say the left plate becomes positively charged. Okay, so we connect the left plate to the positive terminal of a battery, it becomes positively charged. All right, and now let's look at the next picture here. So we have a positively charged plate, so it creates an electric field. So we draw field arrows traveling out from the positive charge towards the other plate. Okay, so arrows traveling from left to right. Now this electric field, it hits the other plate, and we know that an electric field, when it hits moving charges, creates electric force. So the electric field in this picture hits the other plate and it makes the charges in the other plate move away, right? So we end up with a negatively charged plate on the right side. So this method, in this method, there is no direct flow of charges. We don't have any charges flowing from one plate to the other plate. There's a gap in between. However, the charges that accumulate create an induced field, create an electric field. And this electric field charges the other plate by pushing away the charges that were on this other plate here. So the end result is that we end up with a positive plate and a negative plate, but there is no charge flowing in between. So this method is called induction. We are inducing a charge using an electric field. Okay, so in capacitors, this is how charges accumulate by induced by an electric field, but there is no direct flow of charges. Okay. So here we have a parallel plate capacitor. So we have two parallel plates and they carry charge. In our picture, the upper plate carries positive charge, let's say charge of positive Q, and the lower plate carries charge of negative Q. And we draw electric field lines traveling from positive to negative going down. And from what we have done before, we know that when we have parallel plates, field lines are parallel as well. Okay, so the field lines drawn here aren't curves; they travel straight from the positive to the negative plate. Okay, which also means that the field is uniform. Okay, all right. So let's look at the field equation. So this is the field that we have in between the capacitor. So we know that the field is constant, and if you want to calculate the field, this is the equation that we use. It depends on the charge of the plates, the Q, and it depends on a constant, epsilon 0 here, so I'll talk about it. So for now, let's just circle it. Okay, so this epsilon 0, the Greek symbol here, this is called the permittivity of free space, and it has a constant value. So basically it tells us how easily electric field can travel through a medium. So here, this epsilon 0, this symbol here, is the permittivity of vacuum, of free space. So if you have a vacuum between the two plates of the capacitor, we use this value. If you have some other material like water or some other gas maybe, then we use a different value for the permittivity. So let's assume for now that we are using a vacuum, so we'll use this value here. So back to the equation. Electric field between the capacitor depends on Q, the charge Q, the epsilon zero constant, and also A, the area, right? So Q tells us the amount of charge in the system, A tells us the amount of contact between the plates, amount of contact area between the plates, and epsilon zero tells us how easily charge can flow. Okay, so let's circle the A here. So this A tells us the area. Okay, so we have the electric field and we have the charge, and the picture on the left shows the diagram of a capacitor with the electric field line shown and the charge is shown as well. And on the right side, we have the equation for the electric field. Now let's try to calculate the potential difference between these two plates. So we know that when we have two charged objects and they're separated by some distance, they have a potential difference between them. They have a field between them which creates a potential difference. Okay, so this is something that we know from previous lectures. Electric field equals delta V divided by distance. So you measure the potential difference between 2 points and divide by the distance, you get the electric field between these 2 points, assuming that the electric field is constant. Okay, I might as well write this down. All right, so let's put them together. Let's put the two equations together here. So let's combine. Here, let's use a different color. Let's combine the first and the second equation. Let's set them equal to each other, right? So let's draw an arrow for the first equation, draw an arrow for the second equation, set them equal to each other. We end up with a bigger equation. So on the left side, we have delta V C over D. So that's the potential difference between the capacitors. So that's why I put a subscript of C here for the capacitor. So that's on the left side. And on the right side, we have the equation from the previous slide. Q over epsilon 0 times A. All right, and now rearranging the equation, we can solve for Q. This is what we get. Q equals some constants, epsilon 0 multiplied by area of the plates divided by the distance multiplied by delta VC. Okay, so this delta VC, I can draw it on the picture on the slide. So this delta VC is the potential difference between the two plates. All right, so this is how we relate the charge of a capacitor to the potential difference. Okay, and now let's look at the part inside the parenthesis of the equation. So inside the parenthesis, we have a number of constants. We have epsilon 0, A, and D. Okay, and might as well use a different color once again. So this part here is constant because it depends on the properties of the capacitor and on the universal constant epsilon 0. Okay, so I will write constant for this, and it when I say constant, it means it's constant for this particular capacitor. It depends on the properties of this capacitor. Right, it depends on dimensions of the capacitor. All right, so the part in green is just a constant term for the capacitor. So we call it C, capacitance here. Okay, so I'll draw an arrow for this. So this constant C is called the capacitance of this capacitor. And we might just replace everything in the parentheses with big C. So our equation becomes Q equals stuff in the parentheses, that's the big C, times delta V. All right, and let's write this down. So this is called the capacitance. So basically this tells us how much charge a capacitor can hold given a certain potential difference on its plates. Okay, and it depends on the size of the plates, the area of the plates, and the distance between the plates. Okay, so we have our equation here. I'll put this in a, so this is our equation. Q equals CV, right? And C is called the capacitance of the capacitor. Okay, and it's a measure of the capacity to store charge when a potential difference V is applied across the plates of a capacitor. All right, so bigger capacitance means that the capacitor can store bigger charge for the same amount of potential difference. Okay, and the unit of capacitance is called a farad. All right, so big F, a farad here. Okay, so you can also write it as coulombs over volts. That's something you can determine from the equation. Plug in the unit of charge, plug in the unit of volts, and solve for the unit of capacitance. So generally a farad is a large unit. So for practical purposes, we deal with the millifarads and microfarads, capacitors of milli and microfarads. A farad is a large unit, it can store a large amount of charge. Okay, so where do we use capacitors? So it's used in electronics. We'll see in lots of electronic purposes, we need to store charges. Okay, so you can think of a computer. So for computers, usually for desktop computers, where the power supply connects, and if you open up a desktop computer where the power supply connects, you will find capacitors there to store charges. And the reason they're storing charges is because once the capacitors store charges, once you connect a power supply, you charge up the capacitors, you have a certain amount of charges built up. And using these charges, you can change the type of current. You can control the current that you want to send into the motherboard, into the device here. All right, so capacitors provide a way of storing current, storing charges that are coming in, and then distributing them the way you want to. All right, so that's one reason we use capacitors, to store charges, to control current. Okay, so we'll look at some examples. For now, let's look at the problem on the slide. It says we have a potential difference of 1.5 volts. So for example, we have a battery of 1.5 volts, and we apply it across a parallel plate capacitor. So basically we connect the battery to the opposite ends of a capacitor, opposite plates. And we find that the charge in the capacitor is 3 microcoulombs. So connecting a battery of 1.5 volts creates a charge of 3 microcoulombs inside the capacitor. And let's assume that the capacitor is huge. It has area of 10.2 meters square. So that's like the area of a big wall. Okay, so we are looking at a thought problem here. So this isn't a practical capacitor, but nonetheless, let's use it. And we are trying to find the separation. All right. So what do we know so far? We know the V. We know the battery voltage, V, or in this case, the same as the capacitor voltage. And we know the charge stored in the capacitor. That's the 3 microcoulomb. Here, let's circle this. So this is VC. And we have our 3 microcoulomb charge. That's our Q. And we have our area, the 10.2 meters square. And we are trying to find the separation D. All right, so we look at the equation from before. So from the first equation on the slide, it says Q equals CV. So you plug in Q equals 3 microcoulombs. Okay, and remember that you have to convert microcoulombs to regular coulombs. So it's a factor of 10 to the negative 6. And then you plug in V equals 1.5 volts. and then solve for C, we get C equals 2 microfarads. All right, so that's the first step. So we have C, but what we're looking for is the separation D. So we plug in C into the next equation. C equals epsilon 0 area times D, area divided by D, sorry, where epsilon 0 is the constant given, 8.85 times 10 to the negative 12 Coulomb square over Newton meter square in vacuum. All right, and for area and D, you plug in your numbers here. Okay, let's just do it over here. So for capacitance, you plug in sorry, okay, for capacitor, you plug in 2 microfarads. Yeah, there. Capacitance of 2 microfarad, and that's equal to epsilon 0 of, okay, the constant number given. Okay, and an area of 10.2 meters per meter square, and divided by the separation D. Okay, so now you have to solve for D, and when you do that, okay, we get D equals here. So all the number at the top, I'll just put them in parentheses, divided by the capacitance, 2 microfarads, sorry, capacitance. Okay, doing that gives you the separation given. And once again, these are unrealistic numbers because we're looking at a capacitor size that's humongous, 10.2 meters square. So that's not realistic here. Next, we look at the concept of energy stored in capacitor. So we established that capacitors can store charges, and at the same time they can develop potential difference. So we would expect that they also store energy as they develop charges and potential difference. Okay, so before that, let's look at where capacitors are used. Okay, so in nature, you see them in nerve cells. So nerve cells carry a bit of charge, store a bit of charge using properties similar to capacitor. And we can see that the amount of capacitance is tiny, it's 10 to the negative 11. Okay, and then all electronic devices use capacitors extensively because they can store charges. And if you're able to store charges, the charges can be released as required, and there's more control over how charges are released, how the electronic devices function. Okay, so here are some examples here: camera flash, then defibrillators, okay, and computer RAMs, touch screens, and so on. Okay. Now going back to storing energy, so charges are separated in a capacitor, and there's a potential difference. So altogether, it leads to a potential energy stored inside the capacitor. In other words, we have electrical potential energy stored by the capacitors when the plates are charged oppositely. Okay. So let's look at the equation on the slide. It says the change in potential energy, delta U, is equal to Q times delta V. Okay, so energy equals charge multiplied by potential. So change in energy, electrical energy, equals Q times delta V. Okay. And now let's think of the potential difference, the voltage of the capacitor as it charges. Okay, so as the capacitor starts getting charged, it starts from 0 charge and reaches up to a maximum charge. Okay, so the charge itself is increasing, which means the amount of potential energy also increases. Okay, so the potential energy doesn't go from 0 to 100% as soon as you turn on the capacitor. It follows a gradual path. So we have to calculate this potential energy. To calculate the potential difference, we have to do it a bit differently. Okay, so let's look at the picture on the slide. So this is the initial capacitor on the left. There's a potential difference of 0 volts because the plates are not charged. Okay, and then on the right, we have a fully charged capacitor, 100% charged. So it has a potential difference of delta Vc, and the plates are oppositely charged, positive and negative. So that's the initial and the final state. Now let's look at what happens in between. So that's the picture in the middle. So in between is partially charged. So it has a more charge than it started off with, but it has less charge than the final state. So we have 3 states here: initial, in between, and final. And we have different amounts of charges on the plates, and therefore we have different amounts of potential difference across the plates. Okay, so this is what we have. Potential difference builds up across the plates, and we are trying to pump charges onto the plates as well. So the charges have to overcome the potential difference of the plates to build up on the plates themselves. All right, so whatever is pushing the charges have to overcome the potential difference, the resistance provided by the potential difference of the capacitor. So taking all this into account, we have to calculate the energy stored in the capacitor. Okay, so let's continue in the next slide. Yeah. So we are trying to find the energy stored, and suppose the charge in the capacitor is Q, the final charge in the capacitor is Q, and the final potential difference is delta Vc. Okay, so the equation that we end up with looks like this. Energy stored in a capacitor equals half times the charge times the potential difference. Okay, now if you look at the previous slide, we said that the potential energy equals Q times delta V. But now here we are saying the potential energy equals half times Q times delta V. So where did the half come from? So the half comes from the capacitor not being charged instantly. The half accounts for the capacitor being charged gradually from 0 to 100%. All right, so here, I'll write this down. So the factor of half accounts for the capacitor being charged linearly, not instantly. All right. So that's what the factor of half tells us, that the capacitor builds up charge from 0 to 100% gradually, not doesn't happen instantly. So that's the equation for the energy in a capacitor. Okay, now let's make some substitutions. So we already know the charge in a capacitor equals C times delta V. So that was in one of the earlier slides. So let's substitute. Okay, so let's substitute the Q with C times delta V. Here, let's use a different color. Okay, so let's take this expression, C times delta V, and let's plug it in here. All right, and if we do that, our energy equation becomes different. The energy equation becomes half times C times delta V. So we are substituting for Q and multiplied by the other delta V. So we end up with half times C times delta V square. So that's another equation for calculating the potential energy. So the equation at the top gives us the energy in terms of charge and potential difference. The second equation gives us the potential energy in terms of capacitance and potential difference. And we can do one more. So we can replace the delta V with Q over C. Okay, here I'll write it on the slide. So delta V equals Q over C. And that will give us the third equation. Potential energy in a capacitor equals Q square over 2C. So we have three expressions for the potential energy of a capacitor. Half times Q delta V at the top, then half times C delta V square, that's in the middle, and Q square over 2C, that's the third one. Okay, so this tells us that if you want to change the energy stored in a capacitor, we can change multiple parameters, and we can look at the parameters that show up in the equation. We can change the capacitance C, or we can change the charge Q, or we can change the potential V. All right, so these are the three things we can change to change the energy stored in the capacitor. Here, so the C for capacitance, Q for charge, and V for potential. All right, so three factors that affect the amount of energy stored. Okay, so these factors change the energy stored in a capacitor, which automatically means that if you want to change these properties of a capacitor, the capacitance or the charge or the potential, you have to do work on the capacitor. All right, because so doing work using the concept from the previous slide, let's look at what happens when we disconnect a capacitor. Okay, so we'll see some examples soon. All right, so we have a regular capacitor and it's charged. Okay, and after the capacitor becomes charged, we disconnect it. Okay, so here, so this is what we expect. The capacitor has been disconnected, but the plates are already charged, and the charge isn't going anywhere. You can't destroy charge or create charge, which means the charges will remain on the plates of the capacitor. So we say that the capacitor retains its charge because, like I said, the charge cannot go anywhere. It's still stored on the plates. So even if you disconnect a capacitor, the charge doesn't change. All right, fine. Now let's look at the next item. So what happens when the plates of a disconnected charge capacitor are moved closer or further? So we already know that the amount of charge is not going to change. The plates have a fixed amount of charge, but we are moving the plates closer or further. We are changing the separation between the plates. Okay. So here, this means that we are changing the quantity D here. Let's write this down. Okay, so let's try to figure out what happens. So as we know, as we established, the Q charge is unchanged. And then let's look at the equation for capacitance. The equation for capacitance, it's on the slide, it's the second equation, the second item. C equals epsilon 0 times area divided by distance. So we know that epsilon 0 is the constant, permittive free space, it doesn't change. And we are assuming that the area of the capacitors aren't changing, so A is constant as well. The only factor that does change is the D. okay, because we're moving the plates closer or further. Okay. So D is the only factor that changes, and this tells us if you have bigger D, that the plates are moved further away, then C, the capacitance, gets smaller, and then vice versa. All right, so I guess I can draw a picture here. So if we have the plates further apart like this, we have a smaller capacitance. And if we move the plates closer, we have a larger capacitance. Okay, so we have the same plates and of the same area and the same materials, but just we're changing the separation, and that changes the capacitance. All right, so we know that when we move the plates of a capacitor closer, we have a bigger capacitance and vice versa. Okay, so that still doesn't answer the question in the box, but that gives us an important clue. So far we know that the charge is not changing and the capacitance is getting bigger or smaller. So what happens to the capacitor, to the rest of the capacitors? Okay, so let's look at the potential difference. So potential difference V equals Q over C. That's the equation for capacitance. So if the C is getting smaller or bigger, then the V will get bigger or smaller. Okay, so a smaller capacitance leads to a larger potential difference. All right, so we still have the capacitors charged and disconnected. So and we are just moving the plates further or closer apart. And we see that the amount of charge is unchanged, but the capacitance can be changing and the potential difference can be changing. Okay, and now finally let's look at the energy. So we have energy equals half times Q times V. And from the previous line, from the third up item, we know that V can be changing. V can be getting bigger or smaller, which tells us that energy can be getting bigger or smaller as well. So altogether, we start with charged capacitors that are disconnected, and we move the plates closer or further. And in the process, the energy stored in the capacitor is increasing or decreasing. Okay, and we deduced it by following the steps on the slides. Okay, now an obvious question might arise. So we know that energy cannot be destroyed, cannot be created. And here we have a capacitor that's isolated, and we are just moving the plates. And we say that the energy in the capacitor is changing, it's getting bigger or smaller. Now you might wonder, where does the energy come from? So energy has to come from somewhere. It can be created. Somebody has to input energy or export energy, import or export energy to the capacitor. So where does this energy come from? And it comes from the work done in moving the plates. So think of it, a capacitor consists of two plates that are separated, and we're moving the plates closer or further. So in order to move the plates, somebody has to apply a force, somebody has to push. And by applying this force and by moving it a distance, we are doing work. We are transferring energy to the capacitor. And the net result is that whatever work we do leads to the change in energy of the capacitor. The energy can be bigger or smaller depending on which way we are moving the plates. Okay, so this is how we analyze the energy stored in a capacitor. So we have looked at the energy in a capacitor. Now let's look at what happens if you have multiple capacitors. If we connect capacitors in series and in parallel, similar to what we have done for resistors. All right, so what are capacitors in series? So the definition is the same as what we had for resistors, that we have the same current going through all the capacitors. There is no junction, there is no additional path for the current to take. And for capacitors in parallel, there are junctions. So we start with some current that splits into multiple currents and goes through different capacitors. Okay, so capacitors in series and parallel, you can treat them. You can analyze them the same way that we did resistors. Capacitors in series, you have the same current flowing through, and this, in the case of capacitors, this means that they have the same charge stored. Okay, here let's underline it. Okay. So capacitors in series have the same charge stored because they have to have the same current flowing through them. And then capacitors in parallel have the same potential difference. So just like resistors in parallel, capacitors in parallel have the same potential difference. Okay. So you measured the potential difference across any number of capacitors that are connected in parallel. They will all give you the same potential difference, right? Okay, and you can see that we are talking about charges stored in a capacitor. That's because, as we'll see, the current through capacitor isn't constant; it changes, and as the current changes, it carries different amount of charges because current is really a flow of charges. So what we eventually have is charges stored in a capacitor. So sure, we have some current going through a capacitor, but it's easier to deal with charges stored in a capacitor. So that's why when we talk about capacitors, we usually look at charges. It's easier to deal with. So you can see that on the slide, we have the word charges underlined, charges stored, and we're not explicitly talking about current. Okay, so when you think of capacitors, then we're trying to analyze capacitors in series or parallel, think of charges rather than current. Okay. Right, and the footnote at the bottom says that the charges are really carried by current, so you'd think that they're related, but nonetheless it's easier to think of the concept of charges. So let's start with capacitors in parallel, so it's easier to deal with. So here on the left we have two capacitors, C1 and C2, connected in parallel. Okay, and they have different amounts of charges. The upper capacitor has a charge of positive Q1 and negative Q1, and the lower capacitor has a charge of positive Q2 and negative Q2 on opposite plates. And both capacitors have the same potential difference, delta V. Okay, remember that capacitors in parallel must have the same potential difference across them. Okay, so that's the picture on the left. Now, we take the picture on the left, we redraw it, and get the picture on the right. And on the picture on the right, we have a single capacitor with the capacitance of C equilibrium, okay, and the charge of Q total. So what have we done here? We combine the two capacitors on the left into a single capacitor of equivalent capacitance. Here, let's try it like this. Okay, I'll circle the two capacitors and redraw it using a single capacitor on the right. Okay, so we are simplifying a more complicated circuit consisting of two capacitors into something simpler, single capacitor. All right, fine. So now the question is, we have this equivalent capacitor, the single capacitor. So what is the capacitance of this single capacitor? All right, how can we calculate the equivalent capacitance using C1 and C2? So we did something similar for resistors. We calculated equivalent resistors for series and parallel. So now let's do it for capacitors. Okay, so this is our reasoning in the box below. So let's start with the bullet point, item 1 here on the slide. I'll put a bullet point here. It says the total charge equals Q1 plus Q2. Okay, so total charge on the capacitor on the right, it says Q total in the picture, equals Q1 plus Q2. And that sounds reasonable. If you want to find the total charge, you add up the charges of all the capacitors involved. Okay, and then for Q1 and Q2, we use substitutions here. Okay, I will write this down on the slide. So from the capacitor equation, we know that Q1 equals C1V, C1 delta V. And we know that Q2 equals C2 delta V. All right. So these are equations from that we have seen earlier, and we're going to plug them in into the Q1 and Q2 that we have below. Right. And if we do that, if we substitute Q1 and Q2 with C1 delta V and C2 delta V, we get the next we get the next equation here. Q total equals C1 delta V plus C2 delta V. Okay, I'll put it in a box. And finally, let's factor out the delta V. We get delta V and C1 plus C2 in parentheses. All right. So this is what the total charge is in the capacitor, in the two capacitors combined. Okay, put this in another box. All right, so we got an equation to calculate the total charge in the two capacitors. Okay, so let's look at the next equation. Okay, so I'll put a bullet point here. It says Q total equals C equivalent times delta V. All right, where did we get this from? We got this from the regular capacitance equation. So we know that Q equals CV, charge equals C times delta V for a capacitor. And here we are using this equation for the equivalent capacitor. All right, so we have two expressions for Q total, one by adding Q1 and Q2, and the other from the definition of capacitors, considering the C equivalent to be a single capacitor. And now let's set them equal to each other. Okay, so let's set the two equations for Q total equal to each other. All right, so we have Q total equals delta V C1 plus C2, and that's equal to C equivalent delta V, right? Kind of like this. So now we can cancel out the delta V's, and we end up with what the expression that we're looking for. C equivalent equals C1 plus C2. Put it in another box. All right, so this is the result that we're looking for. If you have capacitors in parallel, then the equivalent capacitance is just the capacitors added together. So C equivalent for parallel equals C1 plus C2. And if you have more capacitors in parallel, you just add them up. All right, next we look at capacitors in series. So on the left, we have two capacitors in series, C1 and C2, and they have the same charge across them, okay, because they had to have the same current. So each has a charge of positive Q and negative Q on opposite plates, but they have different potential differences. Okay, so C1 has a potential difference of delta V1 and C2 has a potential difference of delta V2 across. And like before, let's combine the two capacitors and create a single equivalent capacitance. Right, you can draw this, put in a box like before. And draw it here. Okay, so combine the C1 and C2 into single capacitor C equivalent, and this capacitor C equivalent will have the same charge as the other capacitors because they're all in series, and it will have a different potential difference, delta V equivalent. So like in the previous slide, let's try to find an equation to calculate C equivalent from C1 and C2. All right, so that's our derivation on the slide. So our first equation says delta V equivalent, so that's the potential difference across the equivalent capacitor, equals delta V1 plus delta V2. All right, so remember that when things are connected in series, you add up the potential difference across all the elements in series, it will give you the combined potential difference across the whole combination. So that's what we are doing here. We are finding the delta V equivalent across the entire combination. It's delta V1 plus delta V2. And we substitute the delta V's with Q over C. Okay, here. I'll write this down. So we have delta V1 equals Q over C1. And delta V2 equals Q over C2. Okay, and we're going to substitute them into our equations. All right, so we substitute for delta V1 and delta V2. We end up with the next line here. Delta V1 becomes Q over C1, delta V2 becomes Q over C2, and we can factor out a Q. And inside the parentheses, we'll have 1 over C1 plus 1 over C2. And this whole thing, the whole equation is equal to delta V equivalent. Okay, so we're calculating for delta V equivalent now, and then from there we'll calculate delta C, we'll calculate C equivalent. Okay, put it in a box. All right, and then the next equation, let's look at equation 2 on the slide. It says delta V equivalent equals Q over C equivalent. All right, so we are applying the equation for capacitor for the single capacitor, the C equivalent, and we are saying that delta V equals Q over C. Okay, so the standard equation for capacitors. And now let's combine them. Okay, so like the previous slide, we combine the delta V's, set the delta V's equal to each other. Okay, so delta V equivalent equals Q 1 over C1 plus 1 over C2 . Okay, and that's equal to Q over C equivalent. Okay, kind of like this. All right, so that's our equation. We cancel the Q's on both sides and we solve for C equivalent, and we get this 1 over C equivalent equals 1 over C1 plus 1 over C2. All right, so we got our final result. When we have capacitors in series, and you're trying to find the equivalent capacitance, you have to use the reciprocals. 1 over C equivalent equals 1 over C1 plus 1 over C2. And if you have more capacitors in series, you just add the reciprocals, reciprocals of each of them. All right, so we solve for capacitors in parallel and for series. Okay, so in general, this is what we have. In parallel, you add up all the individual capacitors to get the equivalent, which automatically means that the more number of capacitors you have, the bigger equivalent capacitance you end up with, the bigger the C equivalent. And in series, it's the opposite. You to find the equivalent capacitance, you have to consider reciprocals of all the individual capacitors, which means that if you have more capacitors in series, the equivalent capacitance gets smaller. And you can compare with the rules for series and parallel resistors, and you will see that the opposite. In series resistors, more number of resistors produce the bigger resistance, and in parallel resistors, more number of resistors produces a smaller resistance. Okay, so for capacitors, it's the opposite. Let's look at this problem involving multiple capacitors, a combination of 4 capacitors connected in series and parallel. Okay, and the whole combination is connected to a battery of potential difference of 3 volts. We want to find the charge stored in the capacitor circle. Okay, so the 10 microfarad capacitor, we want to find the charge stored in it, and we are given 5 options. So this is we have a combination of capacitors here. So we deal with it the same way we deal with resistors. We try to simplify the picture to extract information, and then once we have enough information, we go back in the opposite direction and come back to the original picture. All right, so let's do it this way. So let's start with the capacitors marked in red, the 3 microfarad and the 7 microfarad. And we can see from the picture, these two capacitors are in parallel, which means if you want to find the equivalent capacitance of these two capacitors only, we just have to add them. Okay, so the highlighted capacitors are in parallel, and their equivalent capacitance, let's call it C equivalent 1, is 10 microfarad. All right, I guess I can draw it too. Here, let's get the pen. So I'll circle it. This combination has a C equivalent of 10 microfarad. Let's call it C equivalent 1. All right, so that's the first piece here. We combine two capacitors to get the equivalent. Then we are going to redraw the circuit by replacing the two red capacitors with the single equivalent capacitor, C equivalent 1. Next slide. All right, so this is our redrawn picture. We replaced the 7 microfarad and the 3 microfarad with the single 10 microfarad, and we are left with the 5 and the 10 microfarad on the other side. So let's do the same thing. Mark the 5 microfarad and 10 microfarad in green and find the equivalent capacitance. And like before, they're in parallel, so that gives us an equivalent capacitance of 15 microfarad. All right, so here let's call this C equivalent 2. All right, so we have a second equivalent capacitance, and now let's redraw the circuit with both C equivalent 1 and 2. All right, new circuit now. We replaced both the capacitors. We replaced the sets of two capacitors with the 10 microfarad and 15 microfarad. We have two equivalent capacitors. Actually, here, let's mark them. So here in red, we have C equivalent 1. Okay. And in green, we have C equivalent 2. Okay, so 10 and the 15 microfarads. So this time we have the C equivalent 1 and 2 in series. So now if you want to combine them, we have to do the reciprocals. Okay, so we have to add the reciprocal of 10 and the reciprocal of 15, and then from there we get the C equivalent of them together. All right, so let's do it on the slide. Let's color them. Okay. So that's the equation for calculating C equivalent 3, the combined capacitance of the two capacitors shown. Let's plug in the numbers and get the value for C equivalent 3. All right, so we plugged in the numbers. Now let's solve. Okay, so you can use a calculator here, do 1 over 10 plus 1 over 15, you'll end up with 1/6. So 1/6 is the reciprocal of C equivalent 3. So 1 over C equivalent 3 equals 1/6. So you flip both sides and we get C equivalent 3. All right, so 6 microfarad is the combined capacitance of all the capacitors that we started off with, of all 4 capacitors. So this is our most simplified circuit. This C equivalent 3. We have, let's redraw the 3-volt battery with this single C equivalent capacitance of 6 microfarad on the next slide. Like that. So let's try to find the charge stored in C equivalent 3. So basically we are trying to find the charge stored in the entire capacitor combination. And from there, we'll eventually figure out the charge stored in the capacitor of interest. Okay, so we'll use the regular capacitor equation, Q equals CV, right? So this time Q is the charge stored in the entire capacitor combination, the total charge. C is the equivalent capacitance, the 6 microfarad of the entire combination, and V is the battery voltage. That's the voltage across the entire capacitor combination. So let's plug all this in. Okay, so here put the slides, put the numbers on the slide. So C equals 6 microfarads, delta V equals 3 volts for the battery, and we end up with a charge of 18 microcoulomb. Okay, so that's the amount of charge stored in all the capacitors together. Okay, that's not the answer we're looking for, but that's a part of the that's a piece of the problem here. Okay, so we'll take this 18 microcoulomb, the combined charge, and go to the next most simplified circuit. So in other words, we'll go backwards. We have the most simplified circuit here. We'll go to one step back, less simplified circuit. All right, so let's go back one step, and we get C equivalent 1 and 2 back. All right, here let's mark them. So we have the 10 microfarad and the 15 microfarad that we had previously. So this is what we call C equivalent 1 and C equivalent 2. Okay. And we know that the combined charge stored is 18 microcoulomb. Here, let's write this down. All right, so the Q total across everything is 18 microcoulombs. We already calculated in the previous slide. All right, and now let's try to figure out the charge stored in the circle capacitor. Okay, now the circle capacitor doesn't show up in the picture, but we know the circle capacitor is part of the green combination. It's part of C equivalent 2, shown in green. So this tells us we might as well find the charge stored in the green combination. Okay, here, do it on the board. So we are trying to find the charge stored here. All right, how do we do this? So we know that the 10 microfarad and the 15 microfarad are in series. So we have two capacitors in series. And we know that when two capacitors are in series, they hold the same charge. They have different voltages, but they hold the same charge. All right, so this tells us that each of the red and the green, the 10 microfarad and the 15 microfarad, should hold the same charge, 18 microcoulomb. Okay, so you can go back a few slides. We talked about capacitors in series, and we established that because all capacitors have the same current flowing through them as they get charged, they end up with the same charge as long as they're in series. Okay, so this tells us each capacitor here, the 10 and the 15 microfarad, will have a charge of 18 microcoulomb. Okay, so let's write this on the slide as well. All right. So we got the charge 18 microcoulomb. Now let's find V2. Let's find the potential difference across this capacitor. All right. So here, let's call this, I guess, V2. And to find V2, we use the regular equation. Q equals CV. And this time, for C, we are going to use the capacitance of 15 microfarad. And for a Q, we are going to use the 18 microcoulomb. All right, so plug in our numbers here. Plug in 18 for Q2. Plug in 15 for the capacitance of the combination. Solve for V2. And for V2, we get 6/5. All right. So we get a voltage of 1.2 volts across the green capacitor, the green combination. So the battery voltage is 3 volts, and the green combination, the 15 microfarad, has a voltage drop of 1.2 volts, which tells us the red combination should have a voltage drop of 1.8 volts. But for the problem that we're looking at, we are concerned about the green capacitor. That's where the capacitor of interest is located. So we take the 1.2 volts voltage drop and we'll use it in the next slide. So in the next slide, we'll look at the next most simplified circuit. This is what we do. Or actually, we replace the equivalent capacitor to the ones in green with the original form, the 5 microfarad and the 10 microfarad. Okay. And we know the voltage across this combination is 1.2 volts, which tells us that the voltage across each of the capacitors in green should be 1.2 volts. Okay, I'll draw this. So just because the 5 and the 10 microfarad capacitors are in parallel, we automatically know they must have the same voltage. Things in parallel always have the same voltage. So here each capacitor has a voltage of 1.2 volt. Let's look at the circle capacitor, the 10 microfarad. And let's use the regular equation Q equals CV for this capacitor, right? Okay, I'm doing it on the slide now. Use Q equals C V, and let's just call it V2 because that's the symbol that we're using. So this tells us Q must equal C of 10 microfarad and a voltage of 1.2 volts. And we get a Q equals 12 microcoulomb. All right, so that's our answer here. The charge stored in the circle capacitor is 12 microcoulomb. Okay, so you can look at the previous few slides, look at the steps involved. We start with the original circuit and then simplify it to get the equivalent capacitance of combination. So we combine 2 capacitors at a time in this problem. So we do it for the red capacitors and the green capacitors. And then once we have the simplified circuits, the red and the green combinations, we combine them to get the equivalent capacitance of the entire system. All right, so doing that, we can calculate the charge stored in the system using Q equals CV, the equation Q equals CV. So once we have the charge in the entire circuit, we go backwards, look at the less simplified circuits, piece by piece, try to figure out the voltages. And eventually, once we have the voltage, once we have the capacitance, we can calculate the charge stored in the circle capacitor. All right, so next topic we look at combination of capacitors and resistors, are known as RC circuits, resistor capacitor circuits. All right, so let's look at it. Okay, so let's start with the circuit shown. We have a single battery and a single capacitor. So when we connect the circuit, when we let current flow, we have charges flowing from the battery to the capacitor. Now, once again, charges don't flow through the capacitor, okay, because the plates are separated. There is no path for the charges to flow through. But nonetheless, the capacitor does become charged because of induction. Okay, you can look at a few slides back. We talked about how a capacitor gets charged because of induction. So the plates of a capacitor develop charges. Okay. The plates of a capacitor develop charges, and in the process develop potential difference. Okay. So nonetheless, we have a current flowing through the circuit, not through the capacitor, but through the entire circuit. Okay, and this current depends on the battery. Let's look at what happens when the capacitor is getting charged. Okay, so we know that as the capacitor is charging, it's developing a potential difference, a voltage. So let's say you turn on the circuit, you close the switch, and you turn on the current. So at time of 0, immediately when you connect the when you turn on the switch, the capacitor has 0 charge. Okay, so let's assume the capacitor is uncharged, which means it has 0 voltage. All right, so that's what is shown on the slide. And now, because the capacitor has 0 voltage, it behaves like a regular wire, like an ideal wire. Yes. It doesn't have a voltage of its own. It behaves like a wire. So it allows maximum current to flow through. It allows the battery to pump maximum charges, pump maximum current to the system, to the circuit. Okay. So we have the statement written in bold. When a capacitor is uncharged, it acts like an ideal wire and doesn't obstruct the flow of current. It allows maximum current to flow through. All right, so this happens only when you close the switch, at the instant you close the switch. So what happens if you keep the switch closed and let more and more current flow? Okay, so let's look at the next bullet point. What happens after a short time? So let's call it t is more than 0. Okay, so it has been a short time since you connected the switch. So now the capacitor has some charge built up on it. There has been some charge accumulated on the capacitor plates. So it has developed some voltage, V. Okay. So now let's think of what happens. So the battery is trying to push the current one way, but the capacitor is trying to push the current the opposite way. That's because the plates of the capacitor, the positive plate of the capacitor faces the positive terminal of the battery. So in essence, the positive plate of the capacitor wants to push a current the opposite direction to which the battery is pushing it. All right. So the capacitor voltage opposes the battery voltage. That's how we state it. And as a result, the current becomes smaller than what it was before. So initially at time of 0, the capacitor was uncharged and it let maximum current go through. But now the capacitor has itself some charge, so it tries to oppose the flow of charge, and the current is smaller than what it started off with. All right, so the longer you have the circuit connected, the longer you have the switch pressed on, the smaller the current gets. So let's look at what happens after a long time after connecting the switch, after turning on the switch. Okay, so let's look at what happens at time of infinity. So that's the third bullet point. So now we can assume that the capacitor is fully charged, or let's say it's almost 100% charged. So the capacitor voltage must equal the battery voltage. Okay, so the capacitor charges itself until it reaches the battery voltage. It can be more than the battery voltage because the battery is what's pushing the charges into the capacitor. So the capacitor can't exceed it. So the battery and the capacitor end up with the same charge after a really long time. So now what happens? The battery is trying to push the current one way, and the capacitor behaves like a battery now effectively because it holds the charge, holds a potential difference. And the capacitor tries to push the current the opposite direction. So both components, the battery and the capacitor, have the same voltage and they're trying to push in opposite direction. The net result is that we end up with 0 current. Okay, so we say we have the statement in bold again at the bottom of the slide. we have a fully charged capacitor and it doesn't let any current go through. So the capacitor, the fully charged capacitor behaves like an open switch. Okay, so it behaves like a broken wire, doesn't let any current go through. So you can look at the transition there. At time of 0, we have a capacitor that's not charged and it behaves like an ideal wire. It allows maximum current to go through. And as time progresses, the current gets smaller and smaller. And at infinite time, after a really long time, the capacitor gets fully charged and behaves like a broken wire, doesn't let any current go through. So the current starts off at some maximum value and then gradually goes down to 0. So that's what you expect in a resistor capacitor circuit. If you have a circuit consisting of a capacitor and resistor, or multiple resistors and capacitors, you expect the current not to be constant. You expect the current to start off at some value and then end up at a different value. Okay, so these are things we'll see when we're dealing with an RC circuit, a resistor capacitor circuit. All right, let's look at this picture now. We have an RC circuit and we have the resistor and capacitor in series, and we are trying to charge a capacitor. Okay, so we have a battery, we have a resistor of resistance R, and we have a capacitor of capacitance C connected all in series. The battery has a voltage of E, and suppose it starts off with a current of I. So let's look at the different scenarios. Let's look at what happens at time of 0. So at time of 0, you turn on the circuit, and let's assume that the capacitor is not charged. So the capacitor has 0 charge, Q equals 0. And we know from the previous slide, an uncharged capacitor behaves like a regular wire, an ideal wire, and it allows maximum current to go through. Okay, so we say that the capacitor voltage VC is 0 because the capacitor doesn't have any charge, and the battery voltage must entirely drop across the resistor. Okay, so the battery has some certain voltage, and in a closed circuit, in a loop, whatever the battery voltage is, it must be dropping across all the components. In this case, the capacitor has 0 voltage, which means the battery must drop all its voltage across the resistor. So we say the VR resistor voltage is equal to E. Let's put it in a box. Right, and I can also write this, write the argument there, because the battery voltage must equal the resistance voltage and the capacitor voltage. And that's known as Kirchhoff's voltage rule, which was covered a few lectures ago. So all right, so at time of 0, entire voltage drop is across the resistor, and there is 0 voltage drop across the capacitor, and the current, you can treat the capacitor as like a regular wire, an ideal wire. So it's like the capacitor doesn't exist, you can replace it with a wire. And to calculate current, you can use regular Ohm's law. You can do V over R, and the current that you end up with is equal to E, the battery voltage, over resistance. So that's the maximum current you have immediately when you turn on the switch. Okay, so that's what you have for time 0. Now let's look at what happens after a long time, time of infinity. So now we have had the capacitor charging for a long time, so the capacitor is fully charged. Okay, and to calculate the charge, we can use the equation on the slide here, Q equals CE. Okay, so Q is the charge in the capacitor, C is the capacitance, that's a constant for the capacitor, and E is the battery voltage. So the capacitor and the battery end up with the same voltage if it's fully charged. So to calculate the charge, we just factor in the capacitance and the battery voltage. So now that the capacitor is fully charged, it behaves like an open switch. Okay, so an open switch means that there is no current flowing. Right, so if there is no current flowing, it means that the voltage across the resistor must be 0, because we know for a resistor V equals IR. So a resistor can have a voltage drop if there's current flowing through it, and if there's no current, it will have 0 voltage. Okay, so the resistance has 0 voltage, and the capacitor has the entire 100% voltage. Okay, so altogether we have the capacitor fully charged and has a voltage equal to the battery. The resistor has 0 voltage and there is 0 current. Okay, so the current starts off at some maximum value at time 0, and at time infinity it drops down to 0, and in the process the capacitor starts at 0 voltage and builds up to maximum voltage, the battery voltage, and the resistor does the opposite. It starts as maximum voltage E and then goes down to 0. All right, so this tells us what happens when the capacitor is uncharged at time 0 and fully charged at time infinity. Okay, so what happens in between when the capacitor is partially charged? So how do we calculate the current, the voltage, and so on? Okay, so what happens when capacitor is partially charged? So let's look at the argument on the slide. Now, we know that to charge a capacitor, we have to have a current flowing, because the current is really a flow of charges. It starts from the battery, carries charges from the battery, and delivers to the capacitor plates, and the capacitor plates end up with a charge. So capacitor current depends on the charge, okay? Or well, the current determines the charge. And following this argument, let's think of what happens when a capacitor develops a charge. So as a capacitor develops a charge, the charge in the capacitor opposes the flow of current. Well, think of it this way here. A current is just a flow of charges. So the current is flowing onto a capacitor plate that's already charged. So you'd expect the charges to repel each other. And the net result is that the bigger the charge in the capacitor, the smaller the current that flows into a capacitor. Okay? Because there is the opposition, there is repulsion. So we can state, we have the statement on the board, on the slide, that I is proportional to negative Q. So this symbol here between the I and the negative Q is a proportional symbol. So this means that something changes proportionally with the other. When something doubles, the other thing doubles. When one thing triples, the other thing triples. That's what a proportional sign means. So I'm saying here that the current is proportional to negative Q. Okay, and the argument is based on what I was talking about, that bigger the charge on the capacitor, the more opposition there is to the current, and the current gets smaller. Okay, so that's where the negative sign comes in. The negative sign tells us that a bigger current means a smaller charge, or the other way, going the other way, a bigger charge means a smaller current. So that's why I put a negative sign here. Okay, so current is proportional to negative Q. If one is bigger, the other has the negative correlation, gets smaller. Okay, so that's the line in the box. Now let's move on to the next line. Okay, so we're going to replace the current with delta Q over T. All right, so something that we have seen earlier, current equals delta Q over delta T, the change in charge over change in time. So that was how we defined current. So now let's look at what we have in the second line. Let's put it in a box again, different color. So now let's put it in a blue box. In the blue box, we have delta Q over delta T proportional to negative Q. So in words, that means the rate at which the current changes, the delta Q over delta T is the rate of change of current, depends on the negative of the charge existing. So you're dealing with a capacitor charge, and the more the charge in the capacitor, the slower the charge, the slower it charges. Okay. So rate of change of charge in the capacitor is directly proportional to the negative of the existing charge. Okay, let's put the negatives here. Okay, all right. Now again, what does this imply? This implies that as your capacitor gets more and more charged, it will be charging at a slower rate. Okay, so bigger charge means charging at a slower rate. So it's still charging. Okay, it will charge up until it goes to the battery voltage, but it will charge not at the same rate. It will charge slower. Okay, so that's the sort of relationship we are looking at. How the capacitor charges over time. Okay, Okay, it doesn't charge at the same rate. It actually gets slower and slower as the more and more charge builds up. Okay, so there's a the way we express this mathematical relationship is by the exponential function. We say that the charge has an exponential dependence on the time. This is what we're going to look at in the next few slides, the exponential dependence of charge and time, and we'll see also that it also applies to voltage and time. All right, okay? So that's in the following slides. Let's review exponential functions first. So we have two graphs over here. We have a we have a blue graph and a yellow graph, and they're both exponential functions. Okay, so one of them is called an exponential decay, the yellow graph, because it starts from maximum value and then approaches 0. Okay, and this yellow graph, you can see, never actually touches 0. It gets smaller and smaller, but never actually gets to 0. That's how exponential functions behave. They approach some final limit, but they actually never reach there. Okay, so that's an exponential decay. And you can also look at the equation on the left. Here, let's let me show you. So is a color there. All right, so the yellow graph is given by this equation here, which I just shown by the arrow. Y equals A multiplied by e to the negative bx. All right, so what are the A and the E and the B? So A is a constant, regular constant. So is B. Okay, so A and B are just constants. But E, well, it's also constant, but it has a specific value. Okay, it has a value of 2.17. Okay. All right, so it's 2.71, sorry, not 17. Let me correct that. Okay, there. All right, so these are what the symbols mean. So an exponential decay curve has the equation shown. It is y equals some constant, then the exponential function to the power negative of another constant times x. Okay, and this tells us at time of 0 we have start with the maximum value, and then as time progresses it approaches 0. Okay, so this is an exponential decay in blue. All right, and then now let's look at the other graph, the blue one. So that's an exponential growth, sort of. Okay, so this one, like this here. So this graph here is kind of the opposite of the yellow graph. It starts at 0 at time 0, and then it grows, but it doesn't grow indefinitely. It approaches some final value, the dashed line. Okay, so both the graphs, the yellow and the blue, never reach the final value. They just approach it, but they get closer and closer, and actually never reach it. Okay. So these are the two exponential graphs that you're dealing with, the exponential decay in yellow and the exponential and the reverse, the exponential growth, I guess, up to a limit, that's in blue. And you can compare the equations. For the exponential decay, we have y equals a e to the power negative bx, the equation at the top. Okay, so we have an exponential term e, so that's the exponential e to the raised to the power of negative of some constant x. And for the other graph, the one below, we have the a, we have the b and the x, but we also have a term of 1 minus. So inside the parenthesis, we have 1 minus e to the negative bx. And because of this 1 minus term, we have the reverse shape. We have the graph starting from 0 and going up to a maximum value. Okay, so the two equations that we'll be needing, we'll be using to analyze the behavior of a capacitor. All right, now about the constants A and B. So A gives us the maximum value. So whatever the constant A is in your equation, that's the maximum value of either of your graphs. The decay or the growth, both of them will have the maximum value of A. And A and B together determine the slope. All right, so if you have a bigger B, for example, you have a larger value of B, the slope will be bigger. That means your graph will be decaying faster, or it will growing faster. And a smaller value of B means
so
slope will be
back to
smaller.
capacitors.
So your
Let's
graph
make a
will
table
be
that looks like this
decaying
here.
slower. It will take
So we
longer to
start
decay,
with,
or it will be growing
an
slower. It will
uncharged
take longer to
capacitor, okay?
grow.
So
Okay,
we
we'll
have
see
a
examples
capacitor
of
that
that
has a
when
charge
we
of 0.
look at the
We're going to
capacitor
charge
equation.
it and then see what happens. Okay, let's write this down. Uncharged capacitor, we're going to start charging it.
Okay, so let's start at time of 0. So at time of 0, there is no charge in the capacitor. So the potential difference across the capacitor is 0, and the current is maximum. Okay, and then we let it charge all the way until it ends to infinity. So when it's fully charged, it has a potential difference equal to the battery potential difference. Okay, so remember that the potential difference of a capacitor connected to a battery will end up to be equal to the battery potential difference. The voltage, battery voltage, and the capacitor voltage must equal each other when the capacitor is fully charged. Okay, so the final potential difference, the final capacitor voltage is E, the battery voltage. Okay, all right, and we can also fill out the next column. Okay, actually, sorry. Before we get to next column, let's look at the first column here. So what we have is a voltage starting at 0, and it ends up at a maximum of E. And we know from a couple of slides ago that the growth from 0 to the maximum value, 0 to fully charged, should not be linear, should be an exponential growth. That's what we established a couple of slides ago. So we write an equation for the potential difference of the capacitor in terms of time, and this is what it looks like. The delta VC, the capacitor voltage, equals E. Okay, and where do we get the E from? Yeah, we get the E because E is the maximum possible battery voltage. Okay, so that's where the E comes from. Okay, remember that the term at the front in a capacitor equation, in an exponential growth equation, is the maximum value. And then since the voltage is growing, we use the term with the 1 minus here, the 1 and the negative inside the parenthesis. And then if you look at the power of E, we are raising E to the power of negative T over tau. So what's tau? We'll see in a bit. So tau is called the time constant. We'll see more about this. And T is the regular time. All right, so tau is a constant, the E is a constant. So what we have is the voltage of the capacitor changing over time. Starts from 0 at 0 time and goes up to 100% at infinite time. Okay. All right, so we got an equation for the voltage of a charging capacitor. Okay, once again, this is a process of charging. When it's discharging, it's different. We'll see later. Okay, so mark the different symbols here. Okay, so delta V is the potential difference of the capacitor, what we call the capacitor voltage. And E at the front is the final potential difference across the capacitor. So the final potential, the final capacitor voltage. And tau equals is called the time constant. Okay, so it's equal to resistance times capacitance. Okay, now let's do something similar for the current. The current starts off at maximum, and the maximum current is just a battery voltage over resistance. So as we have seen, the capacitor behaves like a wire when it's not charged, and it doesn't figure in the equation. And the final current is 0 because once the capacitor is fully charged, it behaves like a broken wire, doesn't let any current go through. So the current starts at maximum, goes down to 0. So it follows an exponential decay. So this is how we write the current equation. Current equals E over R. Now where do we get the E over R from? We get it from the maximum value. Once again, the term at the front is the maximum value. And we have the E to the negative time over tau, and tau is the same time constant. All right, so if we want, we can also replace the E over R with the current of I0 because really they're the same thing. Okay, so this equation tells us for the current, it starts at the maximum value of I0
at time of 0, and then over time it goes, it approaches 0 current. Okay, it never really reaches 0 current, but it approaches.
All right, now let's look at the term that we used in the previous slide, the time constant tau. Okay, what's tau? It's defined as the equation on the slide. Okay, so it has tau equals RC. So you calculate the resistance of the circuit, calculate the capacitance of the circuit, multiply them, and whatever you get is your tau, is your time constant. Okay, and it's called a time constant because it has units of seconds. So you can use the units of resistance and capacitance, and then simplify, you end up with units of second. So that's why it's called a time constant. And it does affect the rate at which capacitors are charged or discharged. Okay, so the time, the time in its name does have a significance in terms of the rates as well, in terms basically how quickly or slowly something the process happens. Okay, so the time constant determines how long it takes to charge or discharge a capacitor. A bigger time constant means it takes longer, so the charging process is slower, and a smaller time constant means it takes less time, so charging process is faster. Okay, so this is what the tau tells us. Okay, all right, so larger tau means longer time to charge or discharge, so slower rate. And you can also think of it in terms of resistance and capacitor. So look at the box at the bottom. So we know that tau equals RC. So that means if a bigger R or a bigger C, it will lead to a bigger tau. Okay, just think of the equation here. Think of the equation at the top. Okay. Okay, so bigger R or C increases tau. And if you think about it, and think about an RC circuit, if you connect a bigger resistance in a circuit, you expect a smaller current. Okay, and a smaller current automatically means that your capacitor will be charged slower. So in other words, a bigger resistance leads to a smaller current, and at the same time leads to a bigger time constant. Okay, so you can see how that relates to a time constant, how the concept of a bigger resistance relates to a concept of bigger time constant. And similarly, if you have a bigger capacitor in your system, in your circuit, the capacitor will require a bigger voltage to build up sufficient charge. Okay, so we know that V equals Q over C. That's the capacitor equation. So if you end up with if you start with a bigger capacitor in your circuit, you have to wait until you develop enough charge. You have to have enough charge in the capacitor before the capacitor voltage can match the battery voltage. Okay, so to build up voltage in the capacitor, you have to build up more and more charge if you have a bigger capacitor, right? So in other words, a bigger capacitor will take longer to develop enough charge, with longer to charge up, so it will have a longer time constant. Okay, so that's how you relate the concept of a time constant with the effects of a resistor and a capacitor in a regular circuit. More about time constant. So these are the two equations that we had previously. The one with the charging capacitor, the voltage of a charging capacitor, and the current in a charging capacitor. The voltage goes from 0 to E, 0 to maximum, and current goes from maximum to 0. Okay, and in both equations, the time constant tau shows up here. Let's mark it. All right, so let's look at what happens at different points in time. Okay, so we are charging a capacitor, and suppose we measure the time, so we measure the voltage at some time, at a certain point in time. Okay, so let's measure the voltage after time of tau. Here, let's write this down. So remember, tau has units of seconds. So tau does represent a time quantity.
Now let's we are measuring the voltage and the current in the system, and we are measuring it after a time of tau. Whatever tau is for the circuit, we measure the current and the voltage after that much time. So we can say that we can set time t equals tau. Okay, and what happens if we set t equals tau? Okay, so the tau in our equation, sorry, the t in our equation is a different color here. So we're going to replace the t in our equation with tau, like that. And let's do it for the other t as well. Okay, so let's replace both t's with taus. Now, what happens then? Then, if we do that here, let's put an equal sign. So really we end up with a tau at the numerator and a tau at the denominator. Okay, and we have the negative sign as before. Okay, so in the equation we are replacing the time with tau. We are trying to measure the voltage and current at a given point in time that's equal to tau. So we plug it into the equation accordingly, and we see that we end up with two taus that cancel each other and leave us with just -1. Alright, so this is what we have written below. That at the time of tau, the voltage equals this much. E, whatever the battery voltage is, whatever the final voltage is, and then inside the parenthesis we have 1 minus e to the power -1. Okay, so that's how much the voltage is after time of tau. Okay, so we can use a calculator, plug in e to the power -1, and you get approximately 37%, 0.37. So you plug in 0.37 in place of in the equation. Alright, so if you plug in 0.37 and you subtract from 1, you get 0.63. So we see the capacitor voltage equals the E, the final voltage, times 0.63. Or, in other words, when a capacitor is charging, after time equal to the time constant, the capacitor reaches a voltage of 63% of its final voltage. Alright, so the capacitor reaches a voltage of 63% of its final voltage after time of tau. Right, so if the tau is bigger, then it will take longer to reach the 63%. If the tau is smaller, it will take less time to reach the 63%. Okay, so as we discussed before, the tau determines how quickly or how slowly the capacitor is charging. All right. So an important figure to know, 63%. So if you know how long it takes for a capacitor to go from 0 to 63%, that's how long the time constant is. Okay, so I guess in a way it's usually a clever trick to finding the time constant without doing calculation. Just measure how long it takes to go from 0 to 63%. All right, let's do the same for the current. So for the current, for this other equation on the right, we also cancel out the taus. We end up with e to the -1, and e to the -1 in a calculator you can find it to be 37%. Okay, so we have current equals 37% of the initial current. Okay, so when a capacitor is charging, the time it takes for the current to go from 100 to 37% is the same as the time constant. All right, so in one time constant, the voltage goes up from 0 to 63%, and the current goes from 100 to 37%. And this is how we can draw them on graphs. So the graph on the left shows us the voltage on a charging capacitor. And you can see that we have a block drawn over here. Here, let's mark it. So this is 63% of the final value. Let's write it 0.63. And the time it takes to go from 0 to 63% is a time of tau. And similarly, for the current graph, the one on the right, we have 37%, and the time it takes to go from 0 to 30, from 100 to 37% is the time of tau. Okay, so clever ways of finding tau from a graph of a voltage or current. Look at the magic numbers, 63% and 37%. That will help you figure out the value of tau. Okay, so here we have a problem for you. We have three capacitors, well, three RC circuits rather. They all have the same batteries and same resistors, but they have different capacitors. Okay, and we are measuring the capacitor voltage for all three of them, shown by the three graphs 1, 2, and 3. Okay, and as we can see from the graphs, the capacitors aren't charging at the same rate. Okay, so capacitor 1 goes from 0 to maximum voltage in the least amount of time, followed by capacitor 2 and 3. So based on this information, we are trying to rank the capacitances of the three circuits. We are trying to rank C1, C2, and C3. Right, so we have 5 options, and we have the equation for the time constant given below. So let's think of the time constant. So we know that a bigger time constant means it takes longer to for the capacitor to charge. So this tells us that capacitor 3, the one in blue, should have the longest time constant because it's taking longest to charge. And capacitor 1 should have the smallest time constant. All right, so we know how to rank the time constants, 1 being the smallest, 3 being the largest. And the equation tells us that the time constant depends on resistance and capacitance. And also the question tells us the resistance of all the circuits are the same. So that just leaves the capacitors to be different. So this tells us that circuit 3 must have the largest capacitor because it has the largest time constant, and circuit 1 should have the smallest. Okay, so we get option C as our answer. Let's also look at the part that says zoomed in. So let's look at the dashed box here. So we can see that the capacitors are all approaching the final value, the maximum value the upper line. But if we zoom in, we'll always see that the red capacitor is ahead of the other two. So that's because the capacitors are never fully charged. They approach 100%, but they never reach there. They get 99%, 99.9999%, but never 100%. So really, when we say a fully charged capacitor, we don't mean a 100% charged capacitor. We mean like 99.9999. So I'll put a few more nines there. Okay, and as the inset shows, as the zoomed in part shows, the red capacitor will always have a bigger charge than the other capacitors because it's charging faster, and the capacitors never reach their ultimate level, the 100% level. Okay, next problem. So this time we have 3 RC circuits and they have different batteries. Okay, so in the previous slide we had the same batteries, but this time we have different batteries, but we still have identical resistors. We have equal resistors. Okay, and we probably have different capacitors as well. We'll figure it out. So like before, we are given the 3 capacitor voltage graphs 1, 2, and 3. So graph 1 starts from 0 in red, goes up to some maximum value. And then graph 2 starts from 0 as well, goes up to a different maximum value less than what 1 was. And graph 3 starts from 0 as well and goes up to a even smaller maximum value. Okay, so let's draw lines to represent the maximum value. Dashed lines here. Let's start with let's start with the capacitor 1. Draw a dashed line to show the maximum value it reaches. Okay. Okay, so something like this. All right, so let's call this V1 max. Okay, let's do something similar for graph 2. So let's call this V2 max, kind of like that. And the last one, we have V3 max for the third graph. All right, so these are the different maximum values for the 3 capacitors, and we have different maximum values because we are connecting them to different batteries. And remember that the maximum value is determined by the batteries to which the capacitor is connected. The capacitor tries to go up, tries to match the battery voltage. All right, so we got the maximum value, but we still have to rank the capacitors. So let's use the trick that we had before. Let's use the 63% rule. The time it takes to go from 0 to 63% is a time constant. So let's use a different color again. I guess use purple. And let's try to mark 63% for each of the voltages. So for V1, 63% is going to be maybe somewhere over here. Okay. All right, I guess kind of hard to grow. I guess somewhere here. So. Okay. And let's try to figure out the time it takes to go from 0 to 63% for the red graph. Okay. Let's draw something like this. All right, so so just pretend this is a straight line here. Let's call this tau 1. So that's the time constant for graph 1. Let's do something similar for graph 2. Yeah, try to use green. So for graph 2, the maximum value is at V2 max, and let's try to mark as 63% of that. So I guess somewhere here. And we get tau 2 from there. All right, so we got tau 1 and tau 2 approximately. Might as well do tau 3 for the third one. So we have 63% of V3 somewhere over here. And we draw a line, find tau 3. All right, so this is how we do this sort of problem. Draw lines at 63% of the maximum, then figure out where they at what time they reach up this to this value, and that time is your time constant. So this tells us from what we have, graph 1 has the largest tau, followed by graph 3 and then 2. Okay, and using the same logic as the previous slide, they all have the same resistor, so they must have different capacitors. So the biggest time constant should have the biggest capacitor. Okay, and we end up with option C as the answer again. All right, so here we're using the magic number here, as we said, the 63%. But the 63% is going to be different for the batteries for the 3 circuits because we are using different batteries. So you have to find the maximum voltage of each circuit, 2 circuits, each capacitor. Well, let's look at the 2 and 3 problems that we find the 63%. The first problem had identical batteries, so all 3 circuits ended up at the same maximum voltage. So you end up with 3 different voltages. 3 different circuits had 63% different batteries. So and using these 3 of the 3 numbers, these 3 voltages, you can figure out the 3 corresponding time constants. Let's think of what happens if we have the same 3 circuits with the same 3 capacitors but different batteries. Okay, so same resistors and capacitors but different batteries. Okay, and if we did that, we would end up with the graph on the right. We would end up with here, same R and C, but different batteries. Right, so we'll have battery 1 of E1, battery 2 of E2, battery 3 of E3, corresponding to the 3 graphs here, but they will all have the same time constant. Okay, so they, all of them will take the same amount of time to get from 0 to 63%. Okay, here, let's try to sketch it on the graph. So that would be 63% of E1 at the top, then 63% of E2, and 63% of E3. Right. So that's another scenario. What happens if you have the same resistors and capacitors but different batteries? Sure. In that case, you start from 0 voltage and go up to the battery voltage, but they change at the same rate. So they go from 0 to 63% in the same amount of time, in the same time constant. So we have dealt with charging a capacitor in an RC circuit. Now let's look at discharging a capacitor when connected to an RC circuit. Okay. So this is our circuit now. We have a resistor and a capacitor, but no battery. And that shouldn't be surprising, because if we had a battery, the capacitor wouldn't be discharging, it would be charging. Okay. So we have no battery because we are trying to discharge. Also, in this scenario, we need to have a capacitor that's already charged, right? So the capacitor starts off as charged, and then it will discharge by producing a current that flows from the positive terminal to the negative terminal through the resistor. So the capacitor has an initial charge of V0, okay? So this is our setup. At time of 0, the capacitor is fully charged, so it acts like a battery, and it has a charge of V0. Okay, so the amount of charge the capacitor contains equals Q equals CV. So you multiply the capacitance with the V0 and you get your charge Q. Okay, so that's the amount of charge in the capacitor. So at the time of 0, immediately when you turn on the current, the capacitor voltage is equal to battery voltage, and also the resistance voltage is the same as the capacitor voltage. So basically the capacitor acts like a battery. So whatever the battery voltage is, whatever the capacitor voltage is, the same should be the resistance voltage. And the current should be maximum because current equals V over R. Okay. So at time of 0, we have maximum current. Okay, fine. Let's look at a time of infinity. So we have allowed the capacitor to drive a current for long enough, for infinite amount of time. So the capacitor becomes discharged. Okay. So we have all the charges traveling from one end of the capacitor to the other end. So now there is no net charge. There is no charge separation. The capacitor is neutral. So if the capacitor is discharged, it acts like a wire, not like a battery anymore. So basically, we have a circuit with a resistor and an empty capacitor that behaves like a wire. So there is no current in the system and there is no voltage. Okay, so we start off with maximum current and the capacitor fully charged, and we end up with 0 current and the capacitor has 0 charge. So that's what we see when discharging a capacitor in an RC circuit with no battery. So the voltage is decreasing, and like before, it will be decreasing exponentially. So we have to use exponential functions like we did for charging capacitor. How the capacitor decreases, and let's start with the left column, the potential difference. So when we start at time 0, we have maximum potential difference. Let's call it V0, VC0 across the capacitor. And at the end, we have 0 potential difference. And let's write an exponential function for this. We have delta V equals delta VC0, the initial, and with the exponential term e to the negative t over tau. And it's the same tau as before, the time constant. So let's label the terms here. Potential difference at any time t. That's on the left side. On the right side of the equation, we have VC0. That's the initial potential difference, the maximum potential difference. Okay, and for the current, we do something similar. We start off with maximum current. And to calculate maximum current, you use Ohm's law. You just do V over R. Here, let's write this down. All right, and then at the end, there is 0 current when there is no potential difference. So the current also flows in exponential decay. So it's the same equation that we had before for a charging capacitor. Current equals initial current multiplied by an exponential factor. Okay, so what are RC circuits used for? So you can see that RC circuits can control the rate. So it has a time component built into it. We can control the rate of charges flowing using resistance and capacitors. So it's used for circuits that need a timing component. So basically timing electrical circuits. All right, so you can think of car flashers, windshield wipers, and a lot of other applications. And also when you want to control the flow of signals, flow of charges, like in the nerves, you'd consider RC circuits. And not just that, when you want to deliver large amount of charges, like in the older camera flashes, you want to use capacitors and RC circuits. And here's an example using camera flash. So we are given a camera flash that consists of a capacitor of capacitance 100 nanofarad. So that's 100 times 10 to the negative 9. Okay, let's write this down. And we are charging it by 4 1.5 volt batteries connected end to end. Okay, so that's our V. Or well, actually let's call it E because we're dealing with the battery voltage. So 4 times 1.5, that's 6 volts. All right, so we have an E battery voltage of 6 volts that charges the capacitor, and then the capacitor is discharged through a resistance of 300 ohms. All right, so first we charge the capacitor to a voltage of 6 volts. Then we remove the batteries and we discharge it to a resistor of 300 ohms. Okay, so really we're looking at the discharging part because we already know how long it takes, how much the initial voltage was. And the question is asking, when we're discharging, how much time does it take for the current to go from 100 to 1%? Okay, so we are trying to find time. And the time to go from 100 to 1%. Okay, so we can eliminate some of the options right away. So we are dealing with a camera flash, so we expect a really small amount of time. So options D and E are really big amounts, big numbers. So we are looking at 10 to the power 5 seconds. And if you calculate, there will be about a day, more than 24 hours. So we can exclude options D and E. We can also exclude option A because it's really tiny, but for now, let's keep it. So let's use our current equation. We can also use the voltage equation, but current equation is easier. So we are dealing with an RC circuit that's discharging, and the current equation looks like the one shown. I equals I0 e to the power negative t over tau. So that's the current equation when the RC circuit is discharging. Okay, so using this equation, we'll plug in the current that we're looking for, the value of I that we're looking for, and the value of I0, the initial value of I0, then plug in the value of tau and solve for t. Okay, all right, let's do it step by step. So first part, how do you find the left side of the equation? How do you find I, the final current? Okay, so it says the final current for our problem is 1% of the initial current. So this is how we write it. I equals 1 over 100 of I0. Okay, so that's what it means to be 100%, to be 1% of the initial. All right, so that takes care of the left side of the equation. Okay, and our problem is stated like this: find the time when I equals 1% of I0. So let's plug it in. Okay, oops, actually before that, let's find tau first, because we'll need to find tau anyway. So let's find the time constant. How do you find the time constant? We use the equation that we had before, tau equals RC. Okay, and here R is the 300 ohms and the capacitance is the 100 nanofarad. You multiply them, we get a time constant of 3 times 10 to the negative 5 seconds. All right, so we got our time constant. Okay, and just a reminder, this time constant is the time it takes to go from 100% to 37% of the current. All right, so when the current is, when we're looking at the current in RC circuit, it's always decreasing, whether the capacitor is charging or discharging. And the time it takes to go from 100 to 37% is the same as the time constant. Okay, and we can see the time constant here is in the order of 10 to the negative 5, which means that option A is too small. Okay, because we are looking at the time that's a lot bigger than 10 to the negative 5 seconds. Okay, we are looking at the time it takes to go from 100 to 1%, which should obviously be a lot bigger than the time it takes to go from 100 to 37%. Okay, so we exclude option A. We are just left with options B and C. Both are in the order of 10 to the negative 4 seconds. All right, so next slide. Well, let's continue the problem. Let's do the math now. Okay, this is our equation. Actually, let's write down the equation from the previous slide. So in the previous slide, that's was our equation. I equals I0 e to the negative t over tau, and then for I, the final current, we plug in 1% of I0. Right, so this is what we are doing in this box. Okay, so we plug in 0.01 I0 on the left side, and plug in and keep the other terms on the right side. I0 is on the right side. Okay, so we can cancel I0 straight away. Okay, so see the trick in this problem. We don't know what I0 is. We don't know what the initial current is, but we don't have to know. We have to know how much the current changes, but we don't know where the exact value where it started from or where it ended up. We just have to know the fraction by it changed. And we have to know that it changed by 99 from 100 to 1%. So doing this and setting up the problem like this, we can eliminate I0 without even having to calculate it. And the next line of the equation gives us 0.01 equals e to the power negative t divided by the time constant. So this value is the time constant. Might as well write this down. All right, so we are plugging in the time constant that we calculated in the previous slide, 3 times 10 to the negative 5. All right, now we have an equation. On the left side, we have some constant. On the right side, we have e raised to some power of t, and the t is what we are solving for. And to solve this sort of equation, you have to use natural logarithm, the ln. Okay, so I uploaded a PDF on how to deal with exponential functions, logarithms, okay, including natural logarithms. So the thing that you need to know over here is that when you have an equation like this, some constant equals e raised to the power something, and you're trying to find a term that's already in the power, it's helpful to take the logarithm, the ln. Okay, and what happens when you take the ln? Yeah, let's look at the notes at the bottom. So this is the property that we need to use. I'll put in a box. Ln log of e to the x is the same as x. Okay. In other words, whenever you have an exponential function in equation, you take the ln on everything on both sides, and the term that has e in it, the exponential e in it, you take the ln of it, the e goes away. Okay, so that's the property that we're using up here. I'll draw an arrow. Okay, so you can think of the ln canceling out the e, and you're left with just the term in the power, the negative t over 3 times 10 to the negative 5 seconds. Okay. All right. Let me try to let me try to work it out up on the side here. So you end up with this 0.01. Oops. Actually, it should be a log of 0.01, ln of 0.01. Okay, let me get the eraser. Right. Try this once again. Okay, so that's what the equation looks like now. And from there, you're solving for t. So isolate the t, move everything else to the other side, including the negative sign. And multiply by the log of 0.01, ln of 0.01. And you can find the ln of 0.01 using a calculator. So it turns into a negative number. So you eventually end up with the answer on the slide. Okay, so that's your final answer. All right, so equations involving exponential terms. If you're trying to find a term that's present in the exponent, think of taking ln's. Think of using the trick over here. All right. So doing this, we can solve for the time, and as I mentioned earlier, you don't even have to solve for the initial current. You don't have to solve for I0.
Okay.
The I0 cancels away as long as you recognize that the final
words
current
of caution when using the RC circuit equations.
So when you're
using the equation that we talked
the
about, the
time,
exponential equations, the exponential decay or the growth,
make sure that the resistor and the capacitor are in series. Okay. So these equations only apply when they're in series. When they're in parallel, you can do that. We'll see how to deal with resistors and capacitors when they're not in series. Okay. So here is an RC circuit in series. Okay. So in this circuit, you can use the equations that we discussed, depending on whether the capacitor is charging or discharging. But here we have a resistor and a capacitor in parallel. You can't use the equations. All right, so this one was series. And the other one is parallel. Now, what do we do if you have a resistor and capacitor in parallel, like the circuit on the left? Okay, in that case, you can look at what happens when the capacitor is fully charged and when it's uncharged. We know that when the capacitor is uncharged, it has 0 voltage and it behaves like an ideal wire. So basically, you replace the capacitor with a wire and then see what happens to the rest of the circuit. And when the capacitor is fully charged, then the current is 0. That means the capacitor behaves like a broken wire, or also called an open switch. So it's like it doesn't exist. The branch with the capacitor has no current going through it. You can pretend it doesn't exist. Okay, so that's how we analyze circuits where resistors and capacitors are in parallel. Okay, you can look at what happens when the capacitor is fully charged and when it's uncharged. You can just replace them with a wire or a
here's an example.
Or a broken wire. We have the big picture on the right. Has a battery, 2 resistors, and a capacitor, and an open switch. Okay, and it says the switch has been open for a long time. Okay, so now what does that mean? Okay, here let's underline it. So that means the capacitor is uncharged. Okay, because the switch has been open for a long time, that means that the capacitor wasn't charging by itself. It was losing charge, probably to the rest of the circuit. Okay. All right. So essentially it says we have a circuit with an uncharged capacitor and the other components, the resistors, the switch, and the battery. And then you close the switch at time 0. Okay, so at time 0, you close the switch, and then you're given 4 options, A, B, C, D. So the question is asking, when you close the switch at time at time 0, for that instant, for the instant that you close the switch, the big circuit on the right side is the same as which circuit among the 4 choices. Okay. Now, how did you solve this problem? Think of what happens for an uncharged capacitor. An uncharged capacitor is the same as a wire. Let's just call it ideal wire, but really means a regular wire. That means you replace the capacitor with a regular wire and see what the circuit looks like. Okay, so here let's do it on the slide. So I'm going to replace this entire branch, the lower branch, with the wire. All right, so replace the capacitor with the wire because it's uncharged at that instant and the switch is closed. So let's look at the 2 branches now. The lower branch has a wire that has 0 resistance. Okay. And the upper branch has some non-zero resistance. Okay, and we know that if you have 2 branches, one with 0 resistance and the other with non-zero resistance, the entire current flows through the lower branch, the one with the 0 resistance, and there is no current flowing to the other branch. So effectively, the upper branch doesn't exist, and we are left with the single 1 ohm resistor, the 1 ohm resistor in the picture, and an upper branch. Okay. So that looks like circuit B in the choices. Okay, so at time of 0, the given circuit behaves like circuit B. Okay, because you replace the capacitor with the ideal wire. All right, then we can look at what happens for the next part, the next question here. What happens at time of infinity? All right, at time of infinity, well, what does that mean? That means the switch has been closed for a long time, the capacitor is fully charged. And when a capacitor is fully charged, it acts like a broken wire. Okay, like that. All right, so now what do we do? Okay, so now the capacitor is fully charged, which means it doesn't let any current go through. So that's like saying that the branch with the capacitor doesn't exist because there's no current flowing through it. Okay, here, let's clear this part. Okay. Okay, so no current through the lower branch. And all current goes through the upper branch here. So it's like saying that this lower branch doesn't exist, okay, because there's no current flowing through it. So now the circuit looks like the circuit consists of the battery and the 2 resistors in series, and there is no lower branch, there is just upper branch. So the circuit looks like now option A. All right, so that's how we analyze resistor capacitor circuits, RC circuits, when resistors and capacitors are in parallel. Right, here's another example. Think of what happens when the capacitor is fully charged. With the capacitor that's fully charged, uncharged. Okay. So replace the capacitor with the wire or with the broken wire and see what the rest of the circuit looks like. Okay. Okay, let's underline this. So fully charged capacitor means capacitor is like a broken wire. All right, so we might as well cross out the capacitor from the picture, from the entire branch from the picture. Okay, so if you do that, effectively the capacitor doesn't exist, the branch doesn't exist. We are left with the two resistors only, the 1 ohm and the 3 ohm. Okay, and using the 1 ohm and the 3 ohm in series, we have to figure out how much charge is stored in the capacitor. Okay. All right, so eventually we want to use this equation, Q equals C times delta V, right? Now we have the C, we have the capacitance of 10 microfarad. Let's write this down. And let's call this R1 and R3, our two resistors. Okay. So we want to find the delta V across the resistor, the capacitor, sorry, delta V across the capacitor. We want to find the capacitor voltage, and once we find the capacitor voltage, we can multiply by the charge to get the multiply by the capacitance to get the charge. Okay, so we want the C and the delta VC in order to calculate the Q in the capacitor. Okay, fine. So how do you calculate the delta V across the capacitor? We already established the capacitor behaves like a broken wire. So how do you calculate the voltage across a broken wire? Okay. So think of the capacitor and the resistor, capacitor and the resistor of 3 ohms in parallel. So the R3 and the capacitor are in parallel. Here, let's write on the board, on the slide. All right, so R3 and C are in parallel, which means they have the same voltage. Which also means if you find the voltage across R3, that will be the same as the voltage across the capacitor. Okay, so that's the trick we are going to use. Find voltage of R3. Okay, and then the voltage across the capacitor will be the same. Okay, so how do you find the voltage across R3? And for that, we have to redraw the circuit. Okay. Yeah, so the fully charged capacitor acts like a broken wire, so you can remove it from the picture. Effectively, we have a circuit with the 1 ohm and the 3 ohm in the picture in series, and the capacitor doesn't exist. Okay, and we can find the voltage across the 3 ohm using Ohm's law. Okay, so VR3 is equal to current I times R3. Okay, so we know what R3 is. R3 is 3 ohms. So how do you find the current? Okay, and to find the current, you have to look at the entire circuit. All right, so you find the equivalent resistance here. Let's do it on the board again, on the slide again. All right, so we are trying to find the current from the battery going through both resistors. okay, like that. And like we said, the capacitor doesn't exist, so we don't have to consider it. So this current goes through both the resistors because they're in series. It's the same current. So we have to find current equals the battery voltage divided by the combined resistance, the equivalent resistance. Okay. All right, so I equals battery voltage over equivalent resistance. And when two resistors are in series, the equivalent resistance is just the two added together. Okay. All right. So you take the two resistors, 1 ohm and the 3 ohm, R1 and R3. You add them up, you get 4 ohms. That's your equivalent resistance. And you plug that in into the equation, plug into the equation with the battery voltage and current, and solve for current there. All right. So here is the more elaborate steps here. You redraw the circuit with the two resistors, combine them into single 4 ohm resistor, then find the total current by doing delta V over R. So that's 1.5 volts over 4 ohms. You get 0.38 amperes. Okay. So the current in the system going through both resistors is 0.38 ohms. 38 amperes there. Okay, so we found the current. Now back to our previous picture. We have the current. We are trying to find V3 up here. So we'll just use Ohm's law. Okay, so we can use Ohm's law for single resistor or for multiple resistor or for the whole circuit. In the previous slide, we used Ohm's law for the entire circuit. Now we're going to use Ohm's law just for R3. Okay, so that will give us V3. All right, so plug in our numbers and we get the answer, 1.1 volts. All right, so we are not done yet. We found the resistance voltage, and this should be the same as the capacitor voltage because the R3 and the capacitor are in parallel. Yeah, because here, let's write this on the slide. Okay, so here, let's mark down what we know. So let's go back to the capacitor now. So the capacitor voltage is 1.1 volt. Okay, and the capacitance C equals 10 microfarad. So we can plug into the equation for Q. So Q equals CV, where let's plug in C and let's plug in V. And we end up with 11 microcoulomb. All right, so that's the whole procedure. We look at the entire circuit. We recognize that the capacitor is fully charged, and so it behaves like a broken wire. So you can exclude the branch with the capacitor and look at the remaining branches, the remaining components. So it turns out the remaining two resistors become in series. So you can find the equivalent. You can find the equivalent resistance of the entire circuit, assuming that the capacitor behaves like a broken wire. Find the current, and this is the same current going through both the resistors because they're in series. And from this current, you find the voltage drop across one of the resistors, the 3 ohm resistor that's in parallel with the capacitor. So this voltage drop across the 3 ohm resistor should be the same as the voltage drop across the capacitor because they're in parallel. And once we have the voltage drop across the capacitor, we know the capacitance. We plug into the capacitor equation and solve for the charge Q. Turns out to be 11 microcoulomb, option C. So now we have example 2. We have the same circuit as before, a battery of 1.5 volts, 2 resistors, 1 ohm and 3 ohm, and a 10 microfarad capacitor. And this time, we start with a capacitor that's uncharged. Okay, I know this because the switch has been open for a long time. An uncharged capacitor behaves like a regular wire, an ideal wire. All right, so immediately when we close the switch, we can replace the capacitor with just a regular wire, something that looks like this. And it has a current, it has current flowing through it. Okay, like that. All right, so now we have 2 branches, the 3 ohm resistor and the capacitor, but the capacitor behaves like a ideal wire. So essentially, we are shorting the 3 ohm resistor. That means that we have the entire current going through the capacitor because it has essentially 0 resistance, and we have 0 current going through the upper branch. So it's like the upper branch doesn't exist. We just have the capacitor and the 1 ohm resistor. Okay. Now the question is asking what's the current to the 1 ohm resistor. So let's redraw the circuit. Okay, replace the capacitor with a ideal wire. And here is the circuit. Change the capacitor to an ideal wire. And as I said, the 3 ohm is shorted, so it's like the branch with the 3 ohm doesn't exist. Okay, and we have the same current going through the battery, the 1 ohm resistor, and the lower branch. Okay. So we might as well erase the upper branch. Okay, so effectively our circuit looks like this: a single resistor and a battery, and the capacitor still behaves like an ideal wire. So now it's a simple Ohm's law problem. We have the voltage of 1.5 volts, we have a resistor of 1 ohm, and use Ohm's law. Okay. And then plug in our numbers, and we get a current of 1.5 amperes. So this is the current that flows through the 1 ohm resistor immediately when the switch is closed. And of course, the current is not going to be the same all throughout. It starts at 1.5 amperes, but as the capacitor builds charge, the value of the current changes, and eventually we get a smaller current. All right, so that's our summary. For RC circuit equations, you can have exponential growth for the voltage and charge, okay, when the capacitor is charging, and you can have exponential decay for the voltage, the charge, and the voltage and the charge when discharging. And either way, charging or discharging, current will have an exponential decay. Okay, and reminder, this only applies when resistor and capacitor are in series. Okay, if they're in parallel, then no, then it doesn't apply. Then you have to look at the concept of ideal wire and a broken wire. Okay, so for a capacitor, when it's uncharged, it behaves like a regular wire, ideal wire, and when it's charged, it behaves like an open switch or a broken wire. Okay, and we have rules for series capacitors and parallel capacitors that we looked at the earlier part of the lecture.